So first of all, I would like to start with the introduction to the trees. Okay, so here we'll see first of all, in introduction to trees, different aspects of trees. So as we have seen, we studied basically a linear data structure, right? So in a linear data structure, we have basically studied, array, linked list, and so many things. Okay, so where we have seen it's basically a linear access is given, like say in array. Then you study a linked list. Then we studied a stack, and basically we studied a queue. Right. So these are some kind of examples of a linear data structure where we have given here array, a linked list, stack, and queue. So why this is called linear data structure? Because basically a linear access is there for every element. Okay, even though for linked list also there is a linear access or sequential access is given, and so that's why it is called as a linear data structure. So here it is given a sequential access or a linear access. It's not that graphically they look in a single line. It's basically the access of element is sequential or linear. That's why it is called as the a linear data structure. Very important point over here. Now the data structure which we are going to see today is basically a tree data structure, and the tree data structure is not a linear data structure, but it is basically it is a non-linear data structure. Okay, so now even though when we look at a particularly a data structure use, we're selecting a data structure, generally we see what things to be used, or for what purpose basically I am selecting a particular data structure, and that is very important, right? So whenever I actually look at for a particular thing, I generally see a few points for what purpose the particular data structure is there. So points are generally selecting a data structure. The first point here is we decide what needs to be stored in given data structure. What needs to be stored. Second thing, the cost of operation on given data structure. Next thing, a memory usage, how much memory it is going to consume. And the next thing is ease of implementation. Ease of implementation. Yeah. So generally, if question comes that, how should I decide which data structure to be used for a given problem statement? So then this is the answer that, what needs to be stored. So which data structure to be used. So first thing is you have to decide what needs to be stored in given data structure. Next is what will be the cost of operation if I use a particular data structure. How much memory is going to use for a particular data structure, and ease of implementation, how much easy to implement a particular data structure. Okay, so these are some important points that generally considered when actually we are selecting a particular data structure for solving or implementing a particular problem. Okay, now let us look at trees. Okay, generally we say how do I use a tree. So generally trees are used for hierarchical applications. Obviously we'll see the application of trees also, but generally the trees are used for a hierarchical application. So let us see one kind of application, or we can say the a kind of a graphical representation of tree. How can we use it? So generally we say the trees is look like something like this. It has branches, something like this. Obviously my painting is not good. And then it has some kind of leaves are there, so branches are there, leaves are there, and this is basically a root of tree. So this is a root of tree, right? Now let's say in similar way, in real life scenario also, the particularly hierarchical structure the trees is arranged. Okay, like let's say here, if I'm drawing here a particular tree of hierarchy, let's say there is a company and the ABC is the CEO of company. Okay, then basically there is a CTO is there, chief technical officer. So let's say that is XY, and then there is a president is there. So this is ABC. AB is president, and then there is vice president, employee, something like that. So hierarchy is maintained, and basically ABC here we basically called it as a root of the tree. Okay, so in real life the tree actually root is on the ground, but here in data structure उसको उल्टा करते हैं, और root is basically at the top, and then branches will come here, and then here is basically a leaf nodes. Even if you look at our college also, so there is a director, and after director comes basically there is a deans, then there is a heads, then assistant heads, and then professors. So the hierarchy is there, and to represent basically all this hierarchy, basically we use the tree. So that is one of the application of the tree. Now let us look at basically how the different concepts in the trees are there, and how generally we use those particular concepts for representations. Okay, so let's say here I'll draw a particular tree for this particular representation over here. So now I'll draw a simple tree over here. We'll go very slowly for initial two lecture. This topic is very important. So I'll draw a simple tree here. So let's say here first node, something like this. I'm drawing the tree now. Like this. Okay, and here I am joining the links between the trees. So you also simultaneously can draw here in your notebook. Okay, now here I'll give some numbering to the nodes. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So let's have given numbering. Now let's see different concepts here. So basically this node is called as the root of the tree. Okay, these are called as nodes which contains the data. Okay, so now let's see one by one the different concepts here. The first thing is about the root of the tree. So here this node is basically the root of the tree. Right, the start node is called as the root of the tree. The next concept is about the children. So here you can see for one node 1, it has 2 and 3 as a children. So 1 is a parent of 2 and 3. Okay, then say node 7 is the children of node 3, or node 7 and 8 is the children of node 3. Okay, then next concept is called as a parent. A parent is basically, it is nothing but it is an ancestor, immediate ancestor of a particular node. Like say here node 4, 5 and 6. So if you look at here, in case of node 4, node 5 and node 6, here the 2 is a parent. It is an immediate ancestor of these 3 nodes. So here 2 is a parent of node 4, 5 and 6. Whereas node 4, 5 and 6, they are the children of node 2. Hope so this concept is clear. The next is about sibling. So sibling is nothing but it is a set of all those nodes who have a common parent. Okay, so it is nothing but it is set of node having the same parent. So node having same parent is called as a sibling. So you can see here node 11 and 12 they are sibling because they have common parent 9. Node 4, 5, 6 they are sibling because they have common parent as 2. Node 7, 8 they are sibling because their common parent is 3. In fact node 3 and 2 here they are also sibling because they have common parent is 1. Okay. Then next is leaf. So leaf is basically a node having no child. It is a node having no child. No child node. Okay. So you can see here node 10 doesn't have any child, doesn't have left child, right child, so it is leaf node. Node 12 doesn't have any child, so it is leaf node. Node 11 doesn't have any child, so leaf node. Like say in the tree also, the last point of tree is a leaf. After leaf there is no further branches, nothing is there. So similar way here also, the node having no child, it is called as the leaf node. Now next is about ancestor and descendant. So we'll see now what is ancestor and descendant. So ancestor. So ancestor is nothing but it is basically a previous all the previous grandparents of a particular child is called as ancestor. So look at here now. The ancestor of node 10. So ancestor of node 10 are node 7, node 3 and node 1. Then ancestor of node 5. So who are ancestor of node 5? Ancestor of node 5 is node 2 and node 1. Okay, towards the root actually we are considering all the nodes coming in the path from that particular node. Then next comes the descendant. Descendant. So descendant of node is nothing but all the remaining nodes towards the leaf node from particular node. Like let's I want to find out descendant of node 3. So descendant of node 3 are node 7, node 8 and node 10. Let's I want to find descendant of 9. So descendant of 9 are 11 and 12. Okay. Now next is cousins. So like say here cousins, those who have same grandparent, like say here node 6, this is node 6 and what you can say node 6 and node 7. Okay, they have same grandparent node 1. Okay, so that's why they are the cousin. Who is the uncle of node 6? Uncle of node 6 is node 3 because you can say father or parent of node 6 is 2. And who is the sibling? Sibling of node 2 is node 3. Right, and uncle ka beta is cousin. So who is a child of node 3? 7 and 8. So 7 are 8 and cousin of node 6. Getting? So in simple language, 2 is a father, 3 is a brother of father, and then 7 is you can say child of the uncle. So that's why 7 and 8 they are cousin of node 6. Okay. So these are some important concepts related to the trees. Okay. So you can note down these points in your language. So in the recursive case, say this is a tree T and tree is generally represented using a recursive data structure. So it is in recursive data structure. So if here I represent here this as a root then obviously all its child, okay, they are also a tree. It has a multiple child and they reflect basically the replica of the tree T1, T2, T3. Okay. So that's why here it is called as a recursive data structure. So tree is called as the recursive data structure. Then there are some more concepts are there. Depth and the height of the tree. So we'll see that depth and the height of the tree. So for this purpose, I'll draw one more tree over here very clearly. So in today's class, we are just going to see different concepts associated with the tree. So I'm drawing here a particular tree. You can also draw here along with me. Okay. So let's say this is a particular tree I've drawn, and I'm giving some numberings here. Let's say number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. This is a root. This is a root of tree. Now say here I've given a particular node X. Now we'll see definition, depth of X. So depth of X is nothing but it is defined as, very important definition, number of edges in path. Number of edges in path from root node. From root node to X. Like say here I want to find out depth of 9. Okay, so number of edges. So this is the circle is here called as the node, and this line which I have drawn here along with arrow, it is called as edges. This is first, second and third. So there are 3 edges from root towards the 9, right? So that's why here depth of 9 is given as 3. Let's say I want to find out depth of 7. So number of edges from root towards 7 is 1, 2 and 3. So that's why depth of 7 given here is 3. You can say here then depth of 7 is 3. Depth of 9 is also 3. So that is number of edges from a root towards a particular node X. Now next is height of X. So how we calculate the height of X? So we'll see here. Height of X. So the height of X is generally given as number of edges in longest path from X to leaf. Very important. Here we find depth from x to root, whereas we find height from x to leaf. Like say I want to find out height of 5. So the largest longest path is basically nothing but the walk that we have here. So from 5, two leaves are there, 10 and 11. So from 5, 7 and 10. So this is one path, 5, 7 and 11 another path. So either number of long edges in longest path is 2. So that's why height of 5 is 2. Height of 2. So here only one edge is there between leaf. So height of 2 is 1. Height of root node. So what is height of root node here? This is one path towards leaf 4. This gives 2 edges. This is 1, 2, 3 and 4. So this gives 4 edges. This is the longest path with 4 number of edges. So that's why this is height of root is 4. And what is the height of tree? What will be the height of tree? So height of tree will be equal to the height of root. Height of tree will be equal to height of root. So here the height of root is 4. So that's why height of tree will be equal to 4. Very important concept here. Okay, so these are some important concepts. So now we'll see the next point about the binary tree. So now next concept we will see about the binary tree. Okay, so now give heading a binary tree. I'll draw here one tree. So this is a tree which I drawn here. The edges I'm drawing now. So a definition of a binary tree is given as a tree in which each node can have at most two children. At most two children. That tree is called binary tree. And look at here every node. You can see this node has a 2 children. This node has 2 children. This node has a 0. This node has 0. This node has 1 children. This node has 2 children. This node has 0 children. This node has 0 children. So that's why this tree it is called as a binary tree. Like say if I draw here another tree like this. This will not be a binary tree. Why? Because this particular node having a three children, and this violates the definition of binary. Bi means 2. So that's why a node can have at max 2 children. Okay. Now let's look at how can we try to represent a particular binary tree and how can we go for implementation. Generally we use basically a dynamic memory allocation or a linked list representation for a given tree. So we'll see now how a tree can be implemented. So there are two ways to implement a tree. One is array and another is a linked list. But I will see using the linked list representation of a particular tree. I'll draw here a particular binary tree. And I'll put some values in it. So I'll be putting here some values. First of all, I'll complete its diagram over here. So you can see in each tree basically it has a certain data. So this is called as a root. Let's say I will put some data over here, or 2, 4, 1, 9, 6, 8, 3, 7. So if I want to represent it in the linked list format or dynamic allocation over here, it has a 3 different cells over here. One is the data, and another is basically the nodes or the edges towards its left and the right child. So here it's a kind of a linked list representation for a particular node over here, and then I'll draw the edges for it. So this is left link, right link, left link, right link, left link, right link, and it has only a left. Okay, I'll just mark it as a left child only. Now we'll put the values over here. Okay. So after putting the values 2, 4, 6, 1, 9, 8, 3, 7. Okay, it's just like simple linked list representation you can see. So how can I define it here, the structure of the node? So simply I can define the structure of node like this. So generally this is called as a root node. So if I want to define the structure for the node here, we can say struct node. Inside node there is a first field is data, then there is a left pointer, nodes left, and there is a right pointer. Okay, so that's how generally we represent a particular tree in the form of a linked list format. Okay, this is in general way what you can say how can we represent a tree. So now let's see some applications of the trees. So give heading applications of tree. The first application here is it is used for storing naturally hierarchical data. Storing naturally hierarchical data. Okay, so a simple example, you can see a file system in your computer. Like say we have one folder, in that another folder is there, like that way. So generally we'll find this application in a kind of Linux, where you can see directly that particular file, or generally give a path. So to maintain that hierarchy, the kind of tree structure is used. Second application is organizing a data let's say organize data for quick search, insert and delete operations. For quick search, insertion and deletion. Okay, so for this generally binary search tree is used. We're going to see in the next class how basically the trees are more efficient than arrays, linked list and other kind of data structures. Okay, the tree representation, how it is much helpful. So we're going to take different cases and numericals on that. The next application of tree is it is used in try. Okay, so generally it is used in dictionaries. So try is basically one of the type of a tree. Also the trees are used in network routing algorithms. So you can see there are so many network routing algorithms are there, and to find out the BSTs, binary search trees, minimum spanning trees, so those kind of trees are used in those kind of the different routing algorithms. Okay, so these are few important applications of the trees. Okay, so now the next topic is about the binary search tree, and before moving ahead you just note down these points.